we're going to do another regression analysis. So we're going to compare the population of the world in the 20th century, starting at 1900 and ending at Y2K, year 2000. So here's the population in millions, and I would like you to plot this in your graphing calculator. So common practice, we could start by using, so this is list 1, this is list 2, aka here's your X values when you graph it, and here are your Y values. However, we often start, when we've got something like this, with saying, we're going to say in 1900, time is 0, time is 10, 20, 30, all the way up to 100. And it just, you can see it's just a transformation. Rather than looking at your graph starting when time is 0, we're looking at our graph starting when time is 1900. And we're only looking for the 100 years. So use your editor, your equation editor, and get this info into your calculator. Okay, for those of you at home, you guys just go ahead and do that. This is what you're going to be doing. You're going to your stat button, option 1, edit, up to your list, and you can clear it so that you can start fresh. And then I'm just going to enter in this data. And then list 2. Oh my goodness. Okay, and then when we have it entered, make sure that your stat plot is on. I've turned mine off at some point, so turn it on. And then here, I guess I want to clear out my graphs, and then set up your window so that you're going to see that data. So my time is starting at 0, and I'm going up to the year 2000. Sorry, this time is starting at 0, and I'm going up to 100. And I'm just going to use an X scalar of 10 since it's every 10 years. And my Y values, well, my smallest population was 1650. I'm just going to go with 1500 Gesundheit. And I'm going to do a scalar of 10, and I'm going all the way up to 6080. I'm going to go 7000. Okay, and when that happens, you're saying I've got a problem in... Oh, thank you. So my min... No, your Y max and Y scale. Your scale 7,000. Yeah, okay, I got it. Okay, so there's our data. So when we look at that data, can we all agree that that's not a linear function we're looking at? And from what we know about exponential functions, we know that they model population growths really well. So when we do a regression analysis on this, we're not going to do a line of best fit, we're going to do an exponential function. Here's where you find that. Go to your stat button. And scroll over to your Calc menu. And if you read down this list, you don't find exponential, you have to keep on going down. So use your arrow keys to go all the way down until you get to option 0, which is exponential regression. I guess it's option 10. and press enter. For some of you, you have to press calculate. I have to press enter twice. Okay, so there's my exponential regression equation. Y equals AB to the x. A is like your P naught, your starting point. So it's like when you did the regression analysis, it's like they're saying this is your initial population, and B is your base. So you've got Y equals A, or P naught. Well, this is what we did in Math 12. Y equals P naught R to the N. So this would be our growth rate. If it's saying that the base is 1.0373, what approximately is our growth rate? At what percent is this population growing? See, that's growing at about 1.4%. Right here, 1.4%. Okay. Okay, so find the regression line. So our regression line is this. Our population at time t is equal to 1447 bracket 1.0, and I'm just rounding off to 3 decimal places to the power of t. Okay, and remember how we could get our calculators to graph that? Let's put it in our notes one more time. So to graph, go to your equation editor, y1 equals. You see that cursor? You're going to press your variables button. And then you're going to go down to option 5, which says statistics. And then you're going to scroll over twice to equation and choose option 1, which is your regression equation. And it just copied it in there for me. So now when I graph it, I can see that exponential growth, my line or my function of best fit. And if you look at a little analysis of that, you can see that it's above your points in this part, and then it comes below the points after. So if you are going to extrapolate, would your extrapolation be above or below the actual? Below, yes. If you were interpolating in this area, would your regression give you an answer above or below the actual? Above. Okay, so then let's solve a word problem here. A half-life. Half-life of strontium is 25 years, meaning that this particular isotope, strontium-90, in 25 years, half of it will decay. So we start with a sample with a mass of 24 milligrams. Let's write an equation for the mass at any time t that remains. So we're looking, what will be the mass at time t? Well, this is like a growth decay problem. We're using this formula. A equals P naught R to the little t over big T. Can you identify your P naught? It's your starting point, 24. What's your rate? Well, we're looking at a half-life. That's telling us the rate is a half. And at any time t, so little t is our variable, and we divide it by the length of the half-life. What is the length of the half-life? Right there, 25 years. That is your capital T. So an equation for the amount of strontium-90 remaining at any time t. So if you have to answer a question like this, where you're given time, you're just filling in for the variable t. Find the mass remaining after 40 years, so t is 40. And that is really just a plug it in your calculator question. Would you all do that right now and make sure that you're using your brackets on your exponent correctly? And you will know you did if you get this to 1 decimal place for your answer. Okay, so 24 bracket 0.5 to the power of bracket 40 over 25. And we should be getting 7.9178. 9170, sorry. Okay, so the next question is different because now it's asking you to find time. That is, like, find the x variable. When you know the mass, you know the y value. So if the mass is 5 grams, we have this problem. 5 is equal to 24 times 1/2 to the little t over 25. And now the variable is in our exponent. How do we solve a question like that? Logs. But before you log, you need to isolate the exponential. Remember, you can't say 24 times 1/2, 12. Why not? BEDMAS, you would have to do the exponent before the multiplication. So rather, let's isolate our exponential, divide both sides by 24. So we've got 5 over 24 is equal to 1/2 to the power of t over 25. Now what are we going to do to each side of the equation in order to isolate the t? We're going to take the log of both sides. Where'd that log come from? It's the inverse operation. Okay, why did we use log? Well, because the power law for logs tells us this exponent can come down in front. So I've got the log of 5 over 24 is equal to t over 25 times the log of 1/2. And if I want to isolate that t, then I'm going to multiply both sides by 25. So I've got 25 times the log of 5 over 24 is equal to t times the log of 1/2, and I'm just going to divide by the log of 1/2 at the same time. So plug that in your calculator and tell me what you get for t. So 25 times the log of 5 over 24, all divided by the log of 1/2, and I'm getting 56.58. Oh, sorry, 56, yeah, let's just say 56.6. And our units here, time, it's in years.